with distinguished experts in the field. Our first session today is on the topic Building Quantum Machine Learning for Image Processing for Sustainable Applications. Our speaker is Dr. Priyanka Kokil, a faculty member at the Indian Institute of Information Technology, Design and Manufacturing, IIIT-DM. She specializes in quantum computing, machine learning, and image processing applications for sustainable technologies. To begin the session, I now invite Dr. Priyanka Kokil to deliver her talk. The stage is yours, ma'am.
Yeah, thank you so much. Thank you, Dr. Deepa ma'am, for inviting me for this event. So today I'm here to give a talk about quantum machine learning. And let me start. I hope that all of you are able to see the screen. Ma'am, is it visible?
Madam. Yes, madam. Yes, madam. Yeah,
okay.
it is visible.
All right. So I just changed the title of the talk a bit. Like instead of just introduction to machine learning, I thought, okay, it might be a little more fancy to say when qubits meet data. Okay, so that makes this machine learning even more powerful. So when we are talking about this particular topic, the quantum machine learning, which is extremely emerging topic and quite fascinating. So I think it's very apt that this event has been planned and it is going on, and like it's a fifth day. It's so wonderful to hear that. Now, the beauty of this particular topic or the research area is not just been identified by the researchers, even United Nations acknowledge the usefulness of this, and they have declared this 2025 as an International Year of Quantum Science and Technology. Right. So last year in June, this declaration came basically. So they have declared this 2025 as International Year of Quantum Science and Technology. So why it is basically important, like why they have noted this thing just to celebrate the 100 years since the start of this development of quantum mechanics. Why it is important? It is important to raise the awareness about the importance of quantum science and technology because it plays a very important role in various aspects of human life as per Quantum 2025 website, if you see. And this was important to draw global attention for various specific issues and encourage collaboration between members, right? Members, states or international organizations and other stakeholders like the companies, the researchers and all. So basically it was, to create the public awareness of the importance of quantum science and its application. And then the main focus of basically to foster the global collaboration and partnership and to support the gender equality in STEM field. With all these things, this year has been declared as Quantum Science and Technology Year, International Year of this. So first, let me congratulate Deepa ma'am for conducting this such a timely conference. All right, so today's agenda is I'll try to introduce the quantum computing, and we'll also try to understand that why it is important to learn this, then machine learning in healthcare, and understanding of quantum machine learning and how it can be used in healthcare, and challenges and some future directions. If time permits, we'll see how it goes basically. So before I go into that, let me tell you what exactly I do here at IIIT-DM Kanchipuram. So I'm heading a lab which is called as Advanced Signal and Image Processing Lab. So here we basically work on filter design, where we talk about the stable filters, the IIR, the infinite impulse response filters we design, and we understand the stability of them in the presence of various parameters which can make the system unstable. So when I say the system, it can be any type of system. It might be your e-bike, it might be your car, it might be a bridge, or any such system where we are looking for some stable solid output, and if it is not working according to the plan, that thing we basically tackle under this topic. Then we have another research area which is biomedical image processing. There we mainly for various type of modalities to find the abnormality, and we try to do that detection in early stage. So right now we are concentrating on ultrasound images and fundus images, but of course we would like to deal with PET images and all that also. Then we have some work on elderly care, where we work for developing the CPAP mask so that it can tackle the condition of sleep apnea. Further, we also work in agricultural domain, where we are trying to develop some deep learning and machine learning enabled solutions for detection of diseases in the plants, especially for the huge plants or the larger plants. Then we have done some work in image quality assessment, where we deal with analyzing the quality of the images and the videos, the endoscopic videos and all, and try to improvise that so that you have better feel of the video if it coming to the OTT platform and all, because we know that the images and videos are very important now, because I mean almost every time we are seeing something, right? So in screen or on TV. So the OTT images, the OTT videos, the images and videos which we are getting in medical domain or otherwise for some entertainment purpose, all the things we try to improvise the quality or assess the quality. Now we are also entering into this quantum machine learning. We are trying to explore more and more about this. All right, so let us see where all it started, right? Where all it started and what we are trying to do. So I hope that you all must be knowing this person. He is Richard Feynman. He is considered to be a pioneer of quantum computing, having proposed in 1982 the idea of quantum computer to efficiently simulate complex quantum systems. And as you can see that is a classical quote by him: nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. He also mentioned that a classical computer will be struggling to simulate quantum phenomena due to inherent differences in their mechanisms, and all these things he has actually mentioned in the papers. By the way, this particular image is from his classical talk, which is very, very popular, which he delivered in 1982 on simulating physics with computers, right? And basically, he given the concept of quantum simulator, which is now a very, very significant research area for quantum computing research. Further, there are three very, very important publications by him. So you can see that this is, of course, a link is also there. These are like in Caltech, it is available. So the first article you can see in 1960, there is a plenty of room at the bottom, where the main focus on the technology which we now call as nanotechnology, to make machines, that includes cars and computers, and now basically up to the atomic level. So in this article, there was no mention or hint of quantum computers, and it was basically totally intended for the people who wanted to pursue a career in physics, elaborating on the potential for progress down at the atomic level. So this was basically from a talk which he delivered in 1959. And then came this very, very main paper in 1982, simulating physics with computers. So this is one of those main papers on quantum computing that most of the people refer. It is more of an abstract view on simulation of physics and what is needed to deal with simulating quantum effects, right? So in fact, in this one, there is no detail on what a quantum computer or quantum algorithm would look like. That is not there in this one. In fact, in this one, there is no mention of qubits or gates. So basically, this particular one was of much interest for the people, from physics domain and who wanted some deeper background on quantum computing. But of course, no mention of quantum computers. So this is basically an output of a keynote speech which he delivered in 1981. And then comes the other article, 1985, quantum mechanical computers. So unlike the previous paper, this particular one was focusing more on the details of how a quantum computer would work and how quantum algorithms would be designed. In fact, in this article also, there is no mention of qubits or gates, right? And yeah, so that is how this particular three important papers are there into the place. Now let us see how it all started. What is the timeline from where to where we have come all the way. So it all started in 1900. It all started with Planck's quantum hypothesis, Max Planck. No, so it started sometime in early 20th century. In fact, this was an era where multiple or several groundbreaking discoveries in the field of quantum mechanics were done. That time it was a great time of key scientists such as Planck, Albert Einstein, Niels Bohr. So these are the key figures who basically contributed a lot for quantum mechanics. And later they also provided a lot of principles for developing the quantum computing. So, okay, so basically in 1900, Max Planck, a German theoretical physicist, introduced the concept of quantized energy levels to explain the phenomena of black body radiation. So what he proposed at that time that the energy is not emitted continuously, rather it is emitted in the form of quanta. So this basically set the mark. It was the beginning of this new era of physics. And from here only the quantum mechanics started. Then you have very important in 1905, Albert Einstein and the photoelectric effect came. It is not there in this diagram basically. So there, Albert Einstein published a paper on photoelectric effect. So he explains the light consists of particles, which is called as photons. And each photon carries a discrete amount of energy proportional to its frequency. So basically, this particular work on photoelectric effect further supported Planck's quantum hypothesis and contributed to the growing understanding of the particle-like behavior of light. So then, like that, it was going. Then 1930, we got Niels Bohr and Bohr model of the atom. Then in 1927, also we had that Heisenberg and the uncertainty principle came. Then 1935, which is another groundbreaking result, came by Einstein, Podolsky and Rosen paradox, which is the Bell's equality, Bell's inequalities. So basically, Albert Einstein, Boris and Nathan Rosen published a paper and they have introduced this ERP paradox. What it does basically, it questioned the completeness of quantum mechanics due to the phenomena of entanglement. And what is entanglement, that I'll be explaining in a while. But I think by now you must be knowing that there is something called entanglement in this one, which is a key resource for quantum computing. Then we have 1964 and the quantum information theory came in 1970s, and then very important conference on physics and computation was held in 1980. Then 1981, 1982, you can see the growth, right? So you can see the growth. You can see that around 1994, we have got two very, very important algorithms, Shor's algorithms and Grover's algorithm. And you can see that around sometime 2020, we have this IBM quantum roadmap came, and nowadays the going on or the ongoing research is definitely of next level, and a lot of people and the industry are working in this direction. So just to give a glimpse that in a single photo, you can see that a lot of great minds, which was a conference, in 1940. And why I wanted to show, because I think that time the conferences must not be that common like how it is nowadays. A lot of conferences are happening. So probably the beauty or the charm of that, attending some conference might not be the same like how it must be there. So, I mean, the photo itself is, it's good to give the goosebumps, right? So great minds in this one. Well, coming to the next, there's a sudden surge in the investment. You can see that the startup activity and the investments in quantum computing have skyrocketed since 2015, right? So till 2015, it was not really, no, it was fine. I mean, there was some investments, but you can see that in 2021, around 2017, 18 and all, it is just shooted like anything. So why it has happened, basically, why this has happened? This has happened because of course, the technological breakthroughs. Then because of that technological improvement, there was an increased enterprise confidence in the commercial viability, geopolitical urgency in national security, because each country, and we can see the current ongoing trend, especially in and around India. We definitely need this. And the growing potential of trillions in economic value across industries, especially for finance and pharmaceuticals, has made this to happen. These are some important points, but not going to discuss too much about it. But yes, you can see that that's a reason that why there is a sudden surge. So of course, it is not just across the world. Even we are not way behind. We're like even the country, even our countries or our government, in fact, to be very specific, they are also spending a lot of money for quantum mission, national quantum mission, and they have allocated a budget of around 6,000 crores for next eight years to scale up scientific and industrial R&D activities for quantum technologies. So quantum mission hub call is there. Today is a deadline for national quantum biotech project. So in all directions, there is a lot of calls are coming in this particular direction. Okay. So if you see, this is again, it's a public investment in quantum technology. Basically, you can see that the private investment and the public investment, of course, private investment has increased, and it is much higher than the public one. Okay, this is something very interesting. I think this you can see the slide, which is showing the progress on patents in this particular direction in quantum technology. So you can see that the total quantum technology based patents are 18,649 for US only from 2000 to 24. And then for Japan, Germany, China, all powerful countries, they are basically having a lot of patents and too much interest in this one. So we are right now not into the list, or at least not in this screen, than the list which I have taken from source. Hopefully we will also be there soon in this list. So you can see that mostly the most of the thing in which direction people are doing work is a quantum computing right now, followed by quantum communication and quantum sensing. So communication is also something very important, that key distribution and all people are working. And then of course, quantum computing for most of the people are working. All right. So now the next question comes that why do we actually need it? Why do we need to talk about this? Is there any problem in the existing system that we have to talk about the quantum machine learning or quantum technology? So actually there is no problem as such, but the problem is the data, the complex data, the massive data, right? The multimodal data. So, or you can say that the huge amount of data. So basically in any domain, if you see nowadays, we have extensive amount of data. So wherever there is a medical data which is massive, complex, and multimodal, it is very difficult to sometimes machines are not supporting. It is taking really a long time, whereas most of the applications, especially in medical, we need quick output, right? So wherever the data is complex and multimodal, we find difficulty because because of the limitations of computational complexity and storage issue, of course. So basically, what quantum computing offers, it gives you speed up, no better speed for high dimensional problems, as well as it is having a very good potential for better diagnosis, drug discovery, and personalized medicine. So that is the main motivation that why no, a lot of research is coming up in quantum machine learning in healthcare. But of course, there is still no some more work is required or more clarity is required that how exactly you are going to implement, how exactly it is going to work, how exactly it is going to run, because we don't have quantum computers right now with us, right? We don't have that facility. Okay. Okay. So if you see, as I said, that there are no, there's a requirement to move, and the requirement is basically nothing but what are the various limitations of classical computing. So for real-time analysis, mainly when you have lot data or no, you need the speed. So that is basically limited by the current resources, or you can say that real-time analysis is limited by classical processing speed. That is one of those problems which we wish to change or tackle by using quantum machine learning. Similarly, the genomic data, that is again of very huge, no, that's again huge. So that large scale genomic data is also very, very difficult to process with the classical computing. And whenever there is a complex image, this always, or too much information is there on the image, then you need high computational resources. So basically, this drug discovery and all these areas where you need faster things, and there only the classical computing faces some limitations. So these things you want to basically tackle with the help of quantum. It is something very similar, like no, in most of the problems, whether you actually need machine learning, whether you need machine learning or you don't need. Similarly, whether you need quantum machine learning or not, that is very important to understand. So that thing you can see, by some comparison. So basically, like in this slide, you can see that there is a comparison of data size versus the processing time for classical systems. So whenever the data is small, like sometime in the range of kilobytes to gigabytes. So basically the time what the classical system takes, it is somewhere between seconds to minutes. It is not very, no, because the data is very small in KB. So there is no significant challenge. Your traditional software and no, machine will be able to handle the information, and processing time will be almost instantaneous. Similarly, if you are dealing with the medium data, which is somewhere in gigabytes to terabytes, right? So still this TB data or GB of data, we are still able to manage the high-end computer. A single high-end computer, it is easy to manage. So simulation or processing might be taking some minutes to hours or some longer time, but still it is fine. And usually the work is basically not restricted by this time. RAM limitation. So that is one challenge which we face. Now, if you are dealing with the further big data, which consists of terabytes to petabytes, where the data is too large to handle, then we need some distributed systems like Hadoop or Spark. And this kind of processing may take from days to some hours to some days. This is a place where basically your classical system faces significant challenges. Then comes the massive data, which is petabytes or beyond. So basically, it even needs something more or better system than large scale classical clusters. So because this kind of data when you are having, or this much data when you are having, you know the processing time goes somewhere from days to weeks or maybe larger. Okay. Okay, so if you see this overview of quantum computing, now we understand that there are some issues are there, the multimodal data is there. No? Multimodal means when the data is coming from multiple forms or from different modes. So basically you might be having the text, you might be having the images or signals or genomic data. So basically when you want to analyze all these varieties of data, then it might be a problem for the classical system. So that is also one such thing which we need to we want, because now again there's one another direction where people are doing research, which is your multimodal data, right? So how do you basically do how do you deal with such huge amount of data? You have to take help of quantum computing. Now when it comes to quantum computing, there are some few terminologies which we need to understand. So quantum computing, when you're talking, meaning that you need to make use of quantum algorithms. Okay, we need to understand what is superposition and entanglement, then error correction, and with all this, it of course proves its supremacy. With the help of quantum computing, hopefully, we will be able to process the data. Now, before I go into the detail of this, further things, let us talk a bit about superposition, some important points which are some important terms which are important in quantum computing. And basically the main power of quantum computing comes from these concepts. So the first concept is the concept of superposition, which gives the superior computing power to the quantum computers. So what basically is this? If you see the current system, what we are having, the system means the current machine or the computer which we are using, it is developed using transistors at the base level. From there you have ICs, and then you have this computer. So basically the system which we are having, in that the data is stored in either yes or no. Either data is there or data is not there. So there are two conditions, either data is there or data is not there. So now this yes or no is something very similar whether you are present in the room or you are not present in the room, right? So it's a fixed state. There is no confusion in this. So whether data is available or data is not available. Now when you are having the data, so whether you are representing it in the form of a voltage or current, because you know that the whatever the IC also you are using, basically you are having some current there or voltage there, which is representing the state. So in whatever way or whatever form you are showing the data, that is either represented by 1 or 0. So 1 means the presence of data, 0 means the absence of data, or data is not there. So these are the two specific state, which also says a binary digit, which in short you call as bit, isn't it? So this is your classical bit. In the existing current system, where you have the computers. If you go a little below, you have ICs. If you go further below, you are having transistors. So basically, transistor stores like this. In contrast, in quantum, we have a state which can take any value, meaning like in this case, either your switch is connected or switch is not connected. Whereas in this case, switch is connected, not connected, or maybe something in between. Okay, or maybe something in between. So meaning that the qubit, which is nothing but the quantum bit, in short, which you call as qubit, can be in the state of superposition, meaning it can be both 0 and 1 at the same time. So this is not just an unknown state, rather it's a combination of both possibilities together, right? Meaning it might be on, it might be off, or it might be off or on. Okay, so there may be a chance that the on probability is higher than the off probability, or there's a higher probability of on or off, all those things. So anything it can be in between. So how do we basically store the information? This is information is stored in 1 second. So this information is stored in basically in the qubit, which it can take any value, right? So it superposition means it can take any value. Like you can see that, for example, if you want to reach to this particular point, right? In the case of 0 and 1 classical bit, either the electron is here or here, no? But in the case of qubit, it can go, some point at x-axis, then at y-axis or something along y-axis to come to this specific point. Let us say this or this or this or this or anything along this trajectory. So any position it can take. This is what you call as superposition, meaning the qubit can have any value. Okay, now there is another important term which is called as interference. So this is why this particular word I'm having here in the slide. It is because this is a consequence of superposition. So as I said that like in the classical computing, you have the fixed state, either it is 1 or 0. But in this case, you may have some probability of 1, you may have some probability of 0, which we call as which we define with the help of which you define the state of the qubit. So that basically may lead to the interference. And what it does basically, if suppose it is constructive interference, then it will enhance the amplitude, of course. If it is destructive interference, it will cancel out the amplitude, right? So basically, this is something important thing. And this interference we use with the entanglement to enable the quantum acceleration, which is we use for quantum computing. Now, what is entanglement? These are two important concepts. So superposition says that the qubit can take any state at any point of time. It need not to be just 1 or 0. It may be anything in between also. Right. Now, what is the concept of entanglement? Entanglement is very interesting concept. It is something which we also experience in our real life sometimes, like when you are trying to remember someone with, or when you remember somebody with your deep thoughts, and suddenly you see there's a call from that guy. So we feel very happy, like though the people might be distance apart, but still their minds are so connected that you remember somebody and they just call, right? So this is what basically is the phenomena of entanglement. It's it's very special and bizarre correlation between two or more qubits basically. So in simple words, you can say that when qubits become entangled, their fates are linked, like how we say it usually in movies and all. This means that the state of one qubit instantly affects the state of its entangled partner, no matter how far apart they are from each other. So for example, and interestingly, this was described by Einstein as spooky action at distance. You can see that this is one qubit, here again another, and then they are just kind of related to each other. So a simple example to understand the concept, let us say there are two entangled balls in this box, right? So you can see that the ball is red on one side and the yellow on the other side. So meaning right now in this particular diagram, you can see that the ball can either be yellow or it can be red. So for now, you can see both the colors. It can either be yellow or red. Here also it can either be yellow or red at the same time. So this is a state of superposition. until you, let us say this girl, and she says that this ball is yellow, and the other guy also sees immediately the ball is yellow. Now, when it is again after some time, when the girl says mine is red, the boy's ball also, he says that is red, means he also sees only red color, right? Meaning, though the balls are not actually linked or related, these are kind of entangled. When she sees it yellow, this also turns to yellow. When she sees red, right? It's a single object which just matches with some other object which is at some distance. Now, if one observer decides to look at their ball from a different angle or side of the box, right? Then, suppose if she decides that she will be looking at the ball from some different angle, then there is a chance that she may see this as yellow or she may see this as red, right? So there's a 50-50% probability of seeing that as yellow or red. Now, when she's seeing it from a different side, there is a chance or there is a possibility that the ball is just turned to yellow. So accordingly, this ball also going to be changed to yellow, right? That is what the concept of entanglement, where the two qubits are just linked to each other in spite of having no space between them, though they may not be directly connected, but still they are connected. It's basically a correlation. So when it comes to the quantum computer, like this, by now you must have heard this term several times, that the quantum computing is working on these two principles of superposition and entanglement. So it is no, it's not basically about how fast your quantum, how fast this it's processing in a traditional sense. Rather, it explores, the quantum computer explores all possible solutions to problem at once, right? So basically what is the meaning is that the quantum computing is trying to amplify the correct answers while cancelling the incorrect ones, right? So you have the good possibility of getting so many correct answers, in that you are going to get a final correct answer. So how do you get that final correct answer? For that, there is something called measurement is to be done. So when we do the measurement, the superposition collapses, meaning the confusion or the in-between, the kind of states collapses, and we get one final correct answer. Okay, so meaning is that there is always some uncertainty or probability is involved. And once you go for measurement is nothing but the collapsing of the final result, you can say, or coming to the collapsing of the superposition to get the final result. So once we get that, we get the correct answer. Now, mathematically, how do we define all these things? How do we define mathematically? So, just a second. Some slide change, it seems. Okay. So this is the slide which should be there. Actually, I'm so sorry for this one. By the way, you can see that when this girl starts seeing this yellow color, the boy also sees the yellow color, meaning that they are just connected to each other, in some ways. So entangled qubits seemingly can transfer information across even light years instantaneously, faster than the speed of light. So as you know that they are not actually connected, so it is not like the directly data is transmitted, rather they are entangled. So that is how we see the information. Just a sec. Okay. So how do we define this qubit state? Let me take tell you some mathematics about this one. Some mathematics behind this. That what is basically qubit? It's a 2-qubit state, meaning that 2 qubits, let us say x and y. So you have 2 states x1, x2, y1 and y2, and we perform this canonical product here, or the tensor product. What it does, it multiplies this x1 with these two, y1 and y2, and x2 also will be multiplied by y1 and y2. So this can be written as x1, y1, y2, x2, y1, y2. And if you multiply individually, x1, y1, x1, y2, x2, y1, x2, y2. This is what you are going to get. Now, one thing is that why you are writing in the vector form. That is something I must say before. Like in the case of classical computing, you have just the number 0 and 1, right? So there is no uncertainty. There is no probability of anything. So it is just a specific 0 and 1. So since it is specific 0 and 1, we just write as a number or variable. Whereas in this case, because the qubit can take any state, it can take 0, it can take 1, it can take something in between, we capture all these things together. And then since you have more numbers, you are going to write this in the form of a vector. That is how we get vector representation in the case of quantum computing. Whereas in classical, we don't use like that. So you're getting x1 and x2. It can take any value. x1 may be the probability of 0, and this is the probability of 1. Similarly, for probability of 0, probability of 1. Here it is not multiplied with any probability, by the way, but you can see here that there is some this notation we are using basically in the case of quantum computing, which is called as bracket, right? Bracket B. It is represented like B1. What is this notation? Bracket 0 plus B2 bracket 1, right? Meaning B1 indicates the probability of getting 0 state plus B2 is a probability of getting 1 state. Now when you are talking about the probability, the normalized value cannot be more than 1, meaning whatever the probability of B1 square plus B2 square, that cannot exceed 1, right? So what we are doing is that we are normalizing the value. It is, and when you do the normalization, it cannot cross 1. So B1 square plus B2 square is equals to 1. Now this B1 can be anything, B2 can be anything, which indicates a probability of getting 0 or getting 1, right? So this is how it is. This is for the qubit state B. Now, if there are 2 qubit A and B, and if you're performing the canonical product like how we did earlier, so you can write down this, the similar way like how we have written here, since it's 2-bit, A1, A2, B1, B2, like that. So A1, A1, B1, bracket 0, canonical product 0, A1, B2, 0, 1, A2, B1, 1, 0, A2, B1, 1, 1. This belongs to C4. What is C4? C is nothing but the complex space where the numbers can take the complex value, because it is not just one. Direction also matters, right? Because it's a spinning of electron what indicates the position. It can be anywhere. It is not just a distance what it is traveling. So how do we define this thing? When bracket 0, canonical product 0, it means that now you have like the 0 canonical product 0. So it means that it is 0 state. So 0 state alone is 1, rest all are 0. When it is 0, 1, the next state is 1, rest all are 0. 1, 0 means 0, 0, 1, 0, and 1, 1 means 0, 0, 0, 1, right? For all this A1, A2, AI or A1 B1 or A1, B2, A2, B1 or whatever it is, all this for any generic value where I replace this by I and j, ai and bj, this modulus of this square cannot be greater than 1. It should be equals to 1 because it's a probability. So this is how it is. The notation, the state A bracket Kronecker product B. You can all, I mean, this particular thing only we are writing in different styles. Like this can be written as bracket AB, bracket AB, or bracket A and then bracket B. Right? This is another example which is called as Bell's state, which represents the maximally entangled quantum state of 2 qubits. Okay, so this you can, this maybe I can skip for the for now. Now, when we understand the concept, okay, very nice that you understand what is a superposition, entanglement, and these things are going to improvise the functionality. It will allow you to get various states in between also, unlike the classical one. But how do we do, or how do we solve all these things, right? So how do you actually bring into the action? So you can see that there are so many interesting algorithms were developed over a period of time. You can see that a lot of algorithms have been developed. Like it started from 1985, Deutsch's algorithm, then Simon's algorithm 1994. But interestingly, these are these are the some initial stage problems for quantum. This actually came for they are really very milestone works. Shor's algorithm and Grover's algorithm, which came in 1994 and 1996. Then we got some HHL algorithm, machine learning algorithms, in recent past, and now it is VQE, and all those things are there. I have taken this from one of the article which was published in Springer. So basically, because these algorithms gives you the way in which you can simplify the things or solve the things, there is a that is how it has brought the things into the picture, and like who can create it first or who can go for it. That is what it is happening now. So okay, so a little bit more about qubit. What is qubit? Qubit is basically, as I said, it's a quantum bit. Collectively, it's not just bit, it is quantum bit, and it is attributed or given by American physicist Benjamin Schumacher. Schumacher, right? So like how the bits are building blocks in your digital logic design, qubits are building blocks for quantum, right? So I think maybe I can just skip. Yeah, maybe this we can see. So there are, of course, there are many different types of bits and qubits, but all qubits must adhere to the law of quantum physics, right? And they should be able to exist in quantum superposition, meaning that they should be able to follow that state of 0, 1 or something in between, right? So like I mentioned already, the classical bit can only have 0 and 1 position, but qubit can take any third state, which is known as superposition state. So, okay, this we understand. Okay, so there is something more here required, by the way. It is like unlike our existing classical systems. When it is coming to the data which you are having, like which we are executing on our classical computers and all, the data, the computer simply process the data in binary code, right? Because you know that whatever information we give in any language, computer simply changes that to binary 0, 1 and all that. And what Now, when you want to process the data, the important thing which comes like when you want to harness the capability of quantum machine learning is the conversion of data. Okay, the classical data must be converted so that the quantum computer can understand, right? So we need some specific kind of encoding to be in place which can convert the classical data which quantum computers can understand. With quantum computers, there is one more thing comes together, that the extreme refrigeration, meaning that the ambient temperature should be maintained for using the quantum computer. So that because the qubit state, it's extremely fragile. It's no, and with very little interference or with very little sound or vibration or anything, it simply changes the position. So we need that, it must be much cooler than the outer space temperature itself. It should be very, very cool, right? So basically, that refrigeration is something also which is a good challenge for quantum computers. Okay. Okay, so yeah, this slide I must have shown you first, by the way, but I'm so sorry for that. Okay, so let me explain this a bit, the single qubit system. A single qubit system, when you're writing, you write A, A1, A2. If it is a classical bit, we simply write A as 1 or 0, right? And they are real value. They are not complex. So here it is in a complex space, A, A1, A2, and I'm writing this in the form of a vector because we want to take uh, account of value 0 as well as value 1. Now, this A1 and A2, which are indicating the probability of existence of state 0 and state 1, this must satisfy the normalization constraint, meaning A1 modulus square plus A2 modulus square should be is equals to 1. More detail about this you can see in this book, Nielsen and Chon, 2011. It's an interesting book, Quantum Computation and Quantum Information. Okay. Now, how this A is denoted here? A is not just a simple A, what we are using in classical computers. We represent it by something called ket. What is this ket? A. Ket A is equals to A1 ket 0 plus A2 ket 1. Now, how do we define this ket 0 state? Ket 0 is represented as 1, 0. Ket 1 is represented as 0, 1. These are the two computational basic states. Now, these A1 and A2 are representing the amplitude, or in other words, you can say it indicates the probability of getting 0 or 1 once you are measuring the state, or once you are doing the measurement of the qubit, you will be knowing the value, which is nothing but A1 square and A2 square, of course, with the modulus sign, because you have the complex value, that is why the space is complex. So the normalization constraint, it says that the possibility, the probability is always 1. And there is something, the conjugate response of, transpose of A, which is represented by this symbol, which is called as bra. So basically, this is bra, and this symbol where this is coming here is called ket, and together we call this as bracket. This is the notation what we are using in quantum computing. So as you can see that this one is bra, and then this one is ket. When the this greater than symbol is here, this is ket, and together we call bracket. So this bracket A is equals to A1 conjugate bracket 0 plus A2 bracket 1 belongs to C square. Okay. I hope it must be clear that just to understand the first thing, that here the data is represented in the form of a column vector to accommodate both the possibilities of zeros and 1 in terms of its probability, and of course it cannot exceed 1. So You know that in classical computing or in the binary digits, what happens is whenever the state is 0, meaning the voltage might be between 0 to, let us say, no, 2. So anything in between 0 to 2, you consider that as 0. Or if anything is beyond 3 to 5 volts, let us say, we call that as state 1. But in quantum, it is not like that. It is much complex interpretation. All right, so you can see here that this is the input state and the evolved state you are presenting by A cap. When I'm saying the evolved state, it is nothing but this bit has been passed through a gate, some gate, like how you are having in the classical computing. In the similar way, we have gates here. So like here you can see the bracket A is applied here, R, Z alpha, R, Y, beta, R, Z gamma. These are nothing but the gates. And this is the final state what we are getting. So how do we apply? Like how we do conventionally, in the similar way, gates are applied sequentially from left to right along the wire. I think this is quite obvious that what is the meaning? It is like 1, 1 or 0 or 20 red is 0, then 20 blue is 1. So head is 0 or tail is 1, like whatever the notation you select to indicate yes or no kind of system. But here it is something in between also. 1 by 3 of 0 plus 2 by 3 of 1. It could be 1, it could be 0 with this possibility or probability. So 8 by 20 might be 0 and 12 by 20 is 1. So similarly with the coin, there's a 50% chance of landing on 0, 50% chance of landing on 1. Right? So basically, and why we are able to have this concept here in place, because this elementary particle, the electron, along with several other properties, it is having one specific property of spin. So it may spin up, it may spin down. So spin up indicates 0, spin down indicates 1. Right? It can spin in two directions, up or down. So this is state 0, this is state 1. Now, a little more about vector or the ket. A vector is just a list of numbers. But when it comes to the quantum, we write this in the form of column vector, which is ket. Right? And if the same information, or if you are writing the information in terms of row vector, you call that as brass. And combination of these two is bracket. Take this example of three-dimensional ket. Ket means column vector, bra means row vector, right? Having four-dimensional, because 1, 2, 3, 4 elements are there. In this case, 3. So who has introduced basically this term bracket? This has come from Paul Dirac. He has introduced this notation. So in the case of column vector, the notation is first the standing line followed by the greater than symbol. Whereas in the case of ket, it is greater than less than symbol followed by standing line. This is what is ket. I'm sorry. This is ket and this is bra. So for any qubit, how do you write mathematically? Unless a classical thing, how do you write mathematically? It is nothing but psi is equals to alpha bracket 0 plus beta ket 1, right? Where alpha and beta are the probability amplitude. It is something, this analogy, where the spinning coin can take any value in between till it is not coming to 0 or 1. So it may be 0, it may be head or it may be tail. That probability is always there in between. Now there is another important concept of coherence time, which is also very important to understand the meaning of coherence. So coherence time is nothing but it's a time duration in which a qubit maintains its fragile quantum state, right? So basically the state which we are interested in, it maintains for a very no less time, very less time. So that time is known as coherence time. So this significantly varies and depends upon the qubit type, and it may vary from microsecond to some longer or something. So why this particular thing is important, that how long the qubit is maintaining the state? Because how long the qubit is maintaining the state is nothing but the superposition. And superposition is a concept which basically allows the quantum computer to execute or perform the computations in parallel, because it can take the value something in between, right? So that allows the performance to happen in parallel. So that is why coherence time is a critical factor in quantum computing. And if there is a noise in the system that may disturb the state of the qubit, and that is called as decoherence. Okay, so we always want the qubit to maintain the state, because longer time will give you more time for performing the complex computation, and error correction time will be available. How do we define mathematically? So basically the coherence time, there are two types, T1 and T2, where T1 is a relaxation time and T2 is a dephasing time. So what is relaxation time? The time it takes for a qubit to lose energy and fall from the excited state to the ground state or the relaxed state. So excited state to the ground state, whatever the time the qubit takes, that is called as a relaxation time. And the time over which the phase information of the qubit wave function is preserved or maintained is called dephasing time. So of course, qubit, the useful state which we are interested in, that is for a very short period of time, and or the dephasing time is of course lesser than the relaxation time. So T2 is always less than or equal to twice of T1. Okay. Now T1, that is the relaxation time which qubit takes to lose its energy and fall from excited state to ground state. And T2, which is the dephasing state, the time over which the phase information of the qubit wave function is preserved. They represent different type of quantum noise. So T1, that is a relaxation time that affects the energy state or population decay, whereas the T2 affects the phase coherence. Okay. So T1 basically indicates the energy loss, and T2 indicates how long the qubit maintains phase coherence. And both of these are important because this time will basically give us the ability to perform the error correction, correct the errors. So why it is important? It is important because we are interested in a longer coherence time, and it is important for us because more quantum operations can be performed before errors occur. Similarly, higher fidelity in quantum gates, then if T2 is more, right, when the phase is maintained, we may have the better error correction and better scalability. So coherence time defines a lifetime of usable quantum information. If a qubit decoheres too quickly, the computations become unreliable and completely fail. So what are the important factors which affect the coherence time? And it is important because we want that useful state to be maintained. So there are so many factors which controls this state. The first one is the environmental noise. Any kind of fluctuation in magnetic or electric field can disturb the qubit state, which falls into the category of environmental noise. Similarly, qubit material and architecture. like trapped ions, spin qubits, or photonic qubit, each having different decoherence sources. Then temperature, of course, it's very important. Quantum computers, as I said, often operates at cryogenic temperature to reduce the thermal noise. And then control precision, poor control electronics can introduce noise and errors that shorten occurrence. So yes, it also impacts the real world application like quantum chemistry simulation, quantum optimization algorithm, and then quantum communication. Okay, so what is this error rate? Is it really important? Yes, definitely it must be important. So what is actually this error? No, why we are talking, like in this particular example, you can see, no, many times we also might have faced something very similar. The power of autocorrect, right? What it does? Let us say you start typing some message in your mobile. You would not believe the day the day I had. I devoured a baby in the cab, right? You what? Huh? Oh God, delivered this phone, I swear. Oh my God. Wow, baby boy or girl? Gorilla. Then again, correction is that it's girl. So basically, in this particular chat, we can see that there are 2 times the spelling mistakes have happened due to the autocorrect. So instead of delivered, it is devoured. And instead of girl, it was gorilla in the first attempt. If it is a chat with your friend, of course, it's not a very big deal. But when it is some official chat or something, these kind of things basically it brings a lot of no. I mean, it will be a very difficult situation in some cases. Embarrassing situation, in fact. So basically, this autocorrect, it's very sensitive at a time, right? In a similar way, this tiny change in temperature can change the calculation, right? So basically, the state of qubit is for that fragile time, and it is affected by so many things. So if there is a, like, for example, if you see there is a mistake happening, no, okay, like if there is a mistake happening in like if you are singing in chorus, if suppose I forget some line somewhere or something wrong, because 10 other people are singing, right, my voice will not be, you cannot perfectly maybe find out that who is singing wrong, or there is some tolerance allowed, there is some tolerance. So basically, there is another important aspect, that how much error you can actually tolerate, okay, which we call as fault tolerance. Meaning, is it the information, is it accurate even when error occurs? Right? That thing we call as fault tolerance. So a fault tolerant quantum computers can complete its calculation correctly even when some qubits are singing the wrong notes. Right? That is what we call as fault tolerance. So this is definitely a prerequisite for quantum computing's most impactful use cases, right? Because there should be some tolerance, of course, like as I said, that a chorus song. But suppose if you are singing alone, then of course it is so eye-catchy. Similarly, how well we can scale the system, meaning can we add more qubits without breaking the computer? Because we know that the qubits are tricky to create, but they are very difficult even for scaling. So more computing power means more qubits, which means that more qubits means more error. And of course, you need a better system to maintain the temperature and all those things, meaning if at any point we are failing, the information will be totally lost. These are different types of qubit technologies, like superconducting qubit can be the trapped ion, spin type, topological, photonic, or neutral atom. So what is no, quantum computing? Basically, whatever we have seen so far is a fundamental base for understanding the concept of quantum computing and machine learning. So quantum mechanics, that's a branch of physics that describes the behavior of these particles at subatomic level. And by now we understand that these two concepts, basically they are the fundamental for quantum computing. One is superposition and the other one is entanglement. Data we have got. We know how to write it mathematically now. And we understand that why do we want to use it, right? Now the next question comes that how do you process it? You got the data, somehow you have represented that in form of qubit. You have maintained the good temperature, you are able to express it in terms of various probabilities, but how do we process the information? So for processing, like how we are having conventionally or classical system, the gates, the logic gates, in the similar way for quantum, we are having quantum gates and circuits. They are very much similar to the classical logic gates, but they operate on qubits, of course. And they manipulate qubit states to perform some specific operations. So there are so many gates, poly X, poly Y, poly Z, Hadamard gate, C0 gate, which is control not, phase shift gate, and all those things. So basically any quantum circuit will consist of these interconnected gates to perform a specific type of operation. Let us see a bit about of this. Okay, so before you go for quantum gates, let us try to first understand what is this concept of Bloch sphere. So Deepa madam, how much time I am having now? Hello madam. Ma'am, may I know how much time I am having? I think it's already 7:22. Can anyone please tell me when is the next session starting?
Yes, ma'am, it is at 7:30.
Okay.
Ma'am, how much time you need, ma'am?
I have a lot more information, but it's okay. I'll close it by under 5 minutes. No problem.
Yes, yes. Till 7:35, it's fine, ma'am, because we started 5 minutes late. Yes, ma'am.
Okay. Okay, so here. Okay. So what is this Bloch sphere? Anyone? Any participants? Can you tell me what this concept is? Okay. Okay, so the first diagram which you can see here, basically, which you can see here is basically the amplitude what qubit can take. Okay, and what we are indicating here is we are indicating only the real numbers. So let us say it is taking along x-axis, it is taking 1, and along y-axis, the value is 0. This point will be 1, 0. And let us say if you see here, this point will be 0 along x-axis and 1 along y-axis. So this is 0, 1. Now, the qubit can be in any state that lies on this unit circle on the plane. Now, what this unit circle is representing? This is basically representing the trajectory what the qubit can take. Okay. So, meaning the qubit can be completely left side, qubit can be completely on right side, or somewhere in between, having some properties of right and some properties of left at the same time. Okay. Now, so like how we represent the complex number, the first term here also we represent the amplitude of zero state, and the second term will indicate the amplitude of the one state. Okay. So okay. So you see here, let us say this. What it is indicating basically. Now, if you see, the qubit is there here, let us say it is 1, 0, and you are measuring all the values and you are monitoring it. So 1, 0 means it is 0 state. So 0 state will be 1 and the 1 state will be 0. So this is represented by 1, 0. Along x-axis it is 1, y-axis it is 0. Now qubit is taking some value in between, let us say 1 by root 2, the possibility of 1, 1 by root 2, the probability of 0 and 1. Similarly, you have this point, the 0 qubit state. So 0, comma 1. This is how we represent. Similarly, this is 1 by root 2 minus 1 by root 2. Now, what is this plus and minus? This basically is nothing but just to indicate the phase, right? The direction in which it is moving, the qubit is moving. So this particular thing is how we will represent. We will represent this by 0, comma minus 1. Okay, with this itself you are able to explain all the possible states for the qubit. Now, just for the sake of completeness, what we will do, we will pick this point, and we'll club these two together. If you stretch these two purple points here, you will be getting like this diagram, right? So everything will be stretched out on a circle. So 1, 0 is as it is. 1 by root 2, 1 by root 2 will come at the top. 0, 1 and 0 minus 1 will come here. They will overlap. And this 1 by root 2 minus 1 by root 2 will come here. Right? This is what I got. This is a trajectory or the path. So generally, how you indicate this state, basically the ket 0 is indicated at the top. The ket 1 is indicated at the bottom. So the ket 0, which is represented as 1, 0, because the full 1, what is 1? 1 into ket 0 means it's a probability of indicating 0. So 1 cannot be there. So 0 into ket 0 plus 1 into ket 1. So this is your ket 0. Similarly, this side, it's a ket 1 probability. This is in between state for one phase, and this is for another phase. Now, in this diagram, if you see what you had, 0, 1 and 0 minus 1 was there on the left hand side, but this particular point we prefer to see at the top. I'm sorry, this particular point 1, 0, because this indicates the 0 probability. So this we want here, and then this you can bring here. So basically, you can rotate the circle in anti-clockwise direction by 90 degree, you will be getting this. 1, 0 at the top, 1 by root 2 here, 0, 1 here, 1 by root 2 and minus 1 by root 2 here. Right? Now, once I have got this dark blue bold line, if you also accommodate the complex numbers, right, the imaginary axis, you will be getting another orange axis, something similar to this, and this green one is your original circle, and this is nothing but it will indicate the position of the qubit, like where exactly the qubit is existing or lying, which we call as Bloch sphere. Okay. So how it is represented, you know that bit is nothing but +1 or -0. Plus and minus is just to indicate that it is 1 and 0. Whereas in the case of qubit, it is 1 and 0. Okay. These are the traditional gates. We know that this is a NOT gate, this is your AND gate, this is your OR gate. So NOT gate is a single input gate. The AND gate A and B, F is nothing but performing the AND operation, means A and A is 0, 0 and 0, 0, 1, 0 is 0, 0, 1 is 0, 1, 1 is 1, and so on. In the similar line, you have the quantum gates, right? So the concept of quantum gates, like the first very fundamental gate we are having, like poly X gate, which is very much equivalent to the NOT gate, the single input gate. This gate was given by Wolfgang Pauli, and this is your single qubit gate, okay, because just single input can come. This is since it is having the the functionality corresponding to NOT gate. This is also called as X gate or quantum NOT gate or bit flip gate. This is one of the fundamental gate, of course. So what it does, it changes the state 0 to state 1 or state 1 to state 0. How do we represent? We represent this by this symbol with the plus sign, the circle on top. And this is the qubit state. When you apply to this poly X gate, you will be getting the flipped qubit. So this is the phase +1. It will be changed to 0 with a minus sign, and -0 if you have applied to the poly X gate, it will be giving you +1. How do we write mathematically the poly X operation? It is 0, 1, 1, 0. Okay. And suppose this get 0, you have passed through X gate, which is your poly X gate, which is equivalent to your NOT gate. This 0 will be converted to 1. 1. Similarly, X1 will be changed to 0. And this is the notation. Simply negates the qubit. How do we do mathematically this operation? So suppose you have this state 0. As I said, it will be changed to 1 or vice versa. So how does it work? So this 0, 1, 1, 0 is your poly X gate, and this is the input which you are applying, which is nothing but state 0, 1, 0. So 0, 1, 1, 0 dot 1, 0 dot product. So 0 into 1 plus 1 into 0, that gives you 0. 1 into 1 plus 0 into 0, that gives you 1. Similarly here, 0, 1, 1, 0, if you apply 1, 0, 1, 1 is represented as 0, 1 in quantum, right? But in classic, you just represent 1. So this is the notation for get 1, 0, 1. You multiply 0 into 0 plus 1 into 1, this becomes 1. 1 into 0 plus 0 into 1, this becomes 0. Okay. So this is a specific case when you are having 1 and 0 and 1. But suppose you want to generalize this for any specific case where there is a probability of having some 0 and some 1. Replace this 1, 0 by some factor, let us say alpha and beta. So 0, 1, 1, 0, alpha, beta, when we multiply, form the dot product, this gives you 0 into alpha plus 1 into beta, this gives you beta. 1 into alpha plus 0 into beta, that gives you alpha. So this becomes beta and alpha. What is beta and alpha? These are nothing but the probability amplitude, and of course these are the complex number. They belong to complex space. And what do they represent? Beta is nothing but the probability which indicates the probability of measuring the state 1, and alpha is something that indicates the probability of having state 0. So this gives you beta and 0. Now poly X gate. So poly X gate, poly Y gate. Poly Y gate is again a single qubit gate which gives you the rotation by pi radians. So this is indicated as capital Y, 0 minus I 0. So this is nothing but it is represented by capital Y, and the mathematical representation is 0 minus I 0. So what it does, this is like if you are passing this qubit 0 from Y, then 0 I, here there should be a semicolon, basically it's a matrix 0 minus I, here I 0 will be multiplied by 0, 1, 0. So that is nothing but 0 I. And what is 0 I? 0 I is nothing but, meaning it is flipping as well as there is a change in the phase. Similarly, for 1, you can see y1 is nothing but 0 minus I 0, 0, 1 minus I 0. So, I mean, if you multiply this matrix with this 0, 1, you'll be getting minus I and 0. This is nothing but minus I get 0. Likewise, you have another gate which is poly Z gate. So, poly Z gate is represented by matrix 1, 0, 0, minus 1. It flips the sign of the phase of a qubit, right? So, again, this is also your one qubit gate. So what it does, basically, it will leave the qubit, the state of qubit along with x and y axis unchanged. Okay, this is some very important gate, which is Hadamard gate. Hadamard gate is this H. And if you're giving 0 to H, then there is a chance, then what it does, it basically changes it to the other qubit. So it is 0, it will be converting it to 1 or 0, depending on the other control. Okay. So, okay. Yeah. So this is a mathematical representation for this one. I think I don't have time to go for this. And yeah, so this is your control NOT gate or C NOT gate, which basically changes the bit of this, whatever this 1, 0, this is the notation. This is the notation. So it flips this 0 to 1 if this is 1. If this is 0, this will remain unchanged. So you can see here, plus 1 minus 0. So since this is plus 1, this particular qubit will be changed to 1. So if the first line is having 1, then the 1 will remain, this 1 remains as it is 1. This minus 0 changes to other one plus 1. Suppose the first line is having minus 0 and the other bit is minus 0, qubit is minus 0, it will remain unchanged. This is what the controlled NOT, meaning it is performing the NOT operation but in a controlled way. That is why this is called as C NOT gate. Okay. So, madam, I think I have taken extra time. So, yeah.
Yes, ma'am. It would be good if time permitted and you could have taken. The session was very interesting. We will invite you in another session for the remaining slides also, ma'am.
Sure.
Ma'am, yes, ma'am. And thank you so much for your time, for your precious time, spending 1.5 to 2 hours for us. And in fact, you have prepared a lot for the session. It is obvious from the slides. And it shows how your expertise, it reflects your expertise. And thanks so much for sharing so much of information to all the participants gathered here. On behalf of the management of KCG College of Technology, our faculty organizing a team of this AICTE sponsored FDP on quantum computing and quantum machine learning applications. I extend our heartfelt gratitude to Dr. Priyanka Kokul ma'am for taking such an interesting and awesome session for all of us. Thank you, ma'am.
Thank you, ma'am.
I would like to invite our next speaker, Dr. Malati Jawahar. Ma'am, are
We now
you?
move
Yeah, Renuka, you can continue. Yes.
We now move on to our second session of the evening titled Carbon Neutrality 4.0 The Quantum Leap. Our speaker is Dr. Malati Jawahar, Senior Principal Scientist at the CSIR Central Weather Research Institute. She specializes in artificial intelligence, computer vision, and image processing with significant contributions to automated inspection, color matching, and quality control solutions. I now invite Dr. Malati Jawahar to take us through her session. Ma'am, over to you.
Malati, ma'am.
Hello.
Yeah, hi, ma'am.
Good evening. I have connected myself in my mobile. Can you share the slides, please? I will rejoin. Just a minute. Hello. Very good evening to one and all. I'm very sorry for the delay. I had a small glitch in my system. So that is the reason that I'm not able to present from my system. So today here, I'm Malti Jawahar presenting about the carbon neutrality 4, a quantum leap in sustainability. Next slide, please. We'll first look at what is sustainability. And today's topic, what we are going to discuss, is a very hot topic. And this gives you a lot of scope of how you can write a proposal. Since I'm coming from a leather research institute, I will give an example of how this has been traditionally done in the leather industry. However, this framework, you can use it for any industry, because nowadays the carbon footprint is one hot topic that is very much connected with sustainability. So let us first see what is sustainability. So as we all know, the SDG goals that is being very much into our system. Here, the World Commission on Environment and Development states that meeting the needs of the present without compromising the ability of future generations to meet their needs. So basically, what it says is like whatever resources that we have present needs to be preserved so that the future generations' needs are being met. So when we look at the dimensions of the sustainability, actually it is one dimension which we are all aware is environment. That is, we need to reduce the emission that and manage the waste efficiently. There needs to be a shift towards the renewable resources is what we normally look at environment sustainability. Even when we look at the second pillar is the economic sustainability, that is to balance the profitability with resource efficiency is a component that we talk about, and faster competitiveness with while reducing the cost. This is with respect to the economic sustainability, and the last pillar is the social sustainability, that is promoting the equality work conditions and prioritizing the health, safety, and the community well-being. That whoever the employees that are there in the organization, their well-being needs to be taken care. Next slide, please. This is the very fundamental top discussion that we need to have, that is called as life cycle assessment. For any product or any service that you look in the market, this life cycle assessment is one method that we define quantitatively and objectively to evaluate the environment impact of that particular product or service throughout the entire life cycle. For example, when we look at a product, we just doesn't look at the production stage alone. We need to look at the entire life cycle. For example, sometimes when we compare two products during the production, the emission or the what to say, like the environment impact during the production may be less, but when it is used, when it is disposed during the later part of the production, there might be a lot that it is releasing. So the life cycle assessment is one which looks at the entire life cycle, right from the raw material extraction till the disposal of that particular material. So when we say life cycle assessment and carbon footprint, both are actually together. Like the carbon foot life cycle assessment covers the entire parameter, like not only the greenhouse gases, it is also, it covers what is called as the ozone layer depletion, acidification, ecosystem destruction, air pollution, all these parameters are evaluated when we look at the life cycle assessment. So it is a comprehensive evaluation of the environment impact throughout the entire life cycle. Next slide, please. These are basic things that I am giving you so that you will understand the problem, what we are going to discuss. So when it comes to carbon footprint, I mean, what is that carbon footprint is defined as? When we look at the life cycle assessment, it is all, it is a comprehensive evaluation, but the carbon footprint, it is only defining the total greenhouse gases. That is what the difference is. So this is a subset of the life cycle assessment, we can say. So when we look at only the total greenhouse gases, well, when I say total greenhouse gases, that is associated with the product or the service, how much it is measured in terms of CO2 or its equivalent is what we are trying to measure. Next slide, please. So this is our actual topic. What is carbon neutrality? So the carbon neutrality is, the goal is to reduce the emission of the carbon dioxide and offsetting the carbon dioxide released into the atmosphere by the company or by the individual or by the institution. When I say offsetting, I will explain you what it means in the next slide. Here, whatever the, for example, there is an industry or a company, so we start measuring its carbon emission, then reducing the how much the carbon footprint, I mean the carbon dioxide that it is emitted, that in terms of how much they are trying to, for example, they are investing in forestation, they are planting a lot of trees, they are investing in terms of energy efficient projects. So these are all ways in which you can uh, uh, balance your carbon dioxide emission. So you are trying to compensate the emission that is being done, and this is what we try to calculate and balance and see how much the emission is done and how much it is reduced or compensated emission. So together, when we look at it, should be then it should end to a net zero. That is what we call it as a carbon neutrality. We'll see what is the so how being into, we are learning a lot with respect to the industry 4.0. So how this industry 4.0 technologies, the next gen strategies can be used to achieve this net zero carbon emission is by integrating the industry 4 tools like IoT. We can use, we are discussing a lot with quantum computing, machine learning, even the digital twins, the blockchain, big data. All these combined together, we can integrate these tools so that we will be the aim is to achieve a net zero carbon emission. So how do we achieve it so that it becomes a sustainable practice? This is the goal of the entire presentation, and this is what I'm going to teach you today. So the evolution is like first is carbon neutrality 1. What it means is it is just offsetting stage. Means what, we are just having a reactive approach. So for example, let us take an AI infrastructure evolution. Like nowadays, there are a lot of data centers that is being because of the large language models that is coming up. We can see a lot of AI infrastructure being developed. So let us take that as an example. And here, when we see the approach is like whatever the AI company is, they are not modifying anything in terms of their infrastructure. Whereas what they are doing is they are trying to purchase the carbon offset. Like As I told, it can be energy efficient solar project. It can be any renewable energy related projects that they fund. When I say purchasing carbon credits means they are funding towards that, so that they are able to take that as a credit to whatever annual emission that they are doing. So this is the first approach, that is a reactive approach. So actually on paper they are showing that there is a carbon neutral. Actual reduction in on-site emission is not being done in this stage. So here, as an example, training a large language model may consume around 1,200 megawatt hour. Means if it has 500 tons of carbon dioxide emission, then the company should buy 500 tons of carbon credits to balance the emission. This is what is being as a offset. I'm sorry, can you go to the next slide, please? Next slide, please. Yeah. So here, this is the example for offsetting a this is the first evolution of being a reactive approach. Next slide, please. So the next one is the process efficiency. Like we are trying to take a proactive reduction in terms of the emission what has been done. So what is the approach that normally we do here is we try to improve the hardware that is there in the AI infrastructure. We try to do a cooling efficiency. We sometimes when the training is being done, we shift some of the computing to a low carbon energy grid, like a solar panel, some kind of wind energy related things. So where the emission will be less. So this kind of things can be done. And similarly, we can have a model, compressed model, like you can have a pruning kind of thing to reduce the training energy that it takes. So here, when we look at the tools, actually, what we will look at is the power usage efficiency optimization can be done. That is one tool. Then we can look at energy efficient GPUs. The chip level, we try to make it more energy efficient. This is one thing that can be done. So here, actually, what we are trying to do is we are trying to reduce the emission that happens in terms of process, and whatever remaining residual, we try to buy the carbon credits. So this is the second approach that can be done as a carbon neutrality. Next slide, please. The third one is a system integration stage. Like this is a holistic management. What we are trying to do is, for example, when I am doing a LLM training, I embed the carbon accounting into the AI training pipeline itself. So what it will try to do is, it will try to give me an estimate, like training that model. The system itself will give a report on how many tons of carbon emission per epoch it is happening. So this kind of thing can be done, and we can optimize the operations that so that the emissions can be optimized in that level. Here, similarly, we can have IoT sensors to track the real-time power, water, and cooling loads, and we can have sustainable dashboards to show the carbon per training job. So the procurement, for example, any procurement that we have, we can have a energy contracts, like green energy contracts kind of thing, the raw material supplier, whether they have a carbon credit oriented. So these kind of approaches is systematic integration into the system actually. So here we will do a life cycle assessment of the data center as well as the models before and after implementing all these approaches. And the supply chain carbon reporting can also be done so that it is becoming more transparent actually. Next slide, please. So this is the actual carbon neutrality 4, that is the digital and intelligent sustainable stage. So what we are trying to do is, it is actually a predictive as well as an optimized stage. Here we can use the AI QML for sustainable optimization. When even we can use the machine learning algorithms to see when the demand is uh, there is a high demand, and how the GPU utilization can be optimized, how QML can solve the global allocation of the task, like to which data center, to which time, and how which energy model can be used. All this mix, because when we talk about QML, it is more of a multi-dimensional optimization. Algorithms can be managed to minimize the carbon footprint. Similarly, whatever carbon credits that we trade or we offset, so we can have a transparency in that in terms of blockchain. And even we can use, for example, digital twins that will stimulate the carbon energy trade-offs before training. So this is all some of just an example to show, to explain how these things can be done actually. I just took an example so that it will be easy for you to understand in terms of a AI infrastructure. I will just go to a manufacturing industry that is connected to leather and explain you in detail. Next slide, please. So here, as I told, the tools can be to predict the workload and carbon forecasting. We can use machine learning, the multivariate energy resource optimization. We can use QML. So this is like where example I just showed, that a company can have a different data centers, and the QML can assign training to where which region it can assign, to at which period it can assign that training, and what is the net emission that is reduced. So that here actually we will, since we are using IoT kind of things and blockchain for transparency, this will actually show in our dashboards how we have achieved that. So this is how a true carbon neutral infrastructure can be achieved. Next slide, please. So what is the traditional procedure when we look at how this carbon footprint for a product is calculated? Is like we have to define the calculation range of the life cycle. For example, as I've shown here, one approach is cradle to grave. That is from the beginning of the product, right? From the raw material procurement till its disposal, or if it is being recycled, the entire life cycle process will be taken, or it is cradle to gate, like the range of raw material till the production. So this is the second method. So these two are typically used in carbon footprint. So we have to really um, make a boundary. Actually, what is that we are defining for our company or for our process? That is very important in terms of monitoring the carbon footprint. Next slide, please. Next slide, please. So this is actually when we look at the life cycle assessment, there is a ISO standard, that is 14,000 with respect to the environment. And with respect to the societal thing, it is ISO 26000. So here we need to define the goal and the scope and the boundaries, whether it is cradle to gate, that raw material till the production, or cradle to grave, that is the full life cycle. So that we have to define the boundaries, and then we have to collect the data, what is related in terms of input output data, the energy, water, chemicals, transport, waste, all these things matters here. Next slide, please. So once we collect all these data, what we have to do is we have to convert this data into emissions. Like as I told, when we say carbon footprint, it only accounts for the greenhouse gases, that is carbon dioxide, methane, nitrogen oxide, all these things, and how this impacts the climate change. So this is what the evaluation is. So basically what we will try to do is we will try to identify the hotspots, like which process is contributing more emission, and we will have to give a suggestion how that emission can be reduced. This is where apart the actual interpretation of the data comes. So when we look at the carbon footprint monitoring, why should we do is, one is nowadays it becomes a compulsion, like the laws and policies are so strict that not only in the European Union, because we export a lot to the US market and Europe markets, uh, uh, we need to satisfy our clients. So this irrespective of where our factory or where our production is, nowadays this eco labeling is becoming very much aware, and it becomes a very important concept in terms of uh, the branding. When you sell this product, when you have a eco labeling product, definitely the market value is more. So it is advantage to have this kind of monitoring. So what is that limitation that is happening is, this is very data intensive, and it becomes very time consuming when we do very in a traditional way to assess all these things. That is where the technological advancements are required, and this is where the in fact a lot of funding agencies will give funds when you write proposals based on carbon footprint monitoring, irrespective of what industry you want to. Actually, you can sit with any industry that you are. It can be a steel industry, it can be a textile industry, it can be a leather processing industry, but all, irrespective of which industry it is, all the industries needs to have this carbon footprint monitoring. Next slide, please. So I have just given an overview of a typical leather processing industry thing. So I'm not going very in depth into the concept, but a general overview I will give. Here what we have is one is called as the upstream process, one is the core process, another is the downstream process. So here when we look at the upstream process, for example, a leather manufacturing industry means upstream process right from the animal breeding, like uh, uh, from that farming, the upstream process, like how the animal farming is done. No, to just make a small note, the animals are not killed for manufacturing leather. It is actually killed for the meat. Okay, what is thrown as a waste is what is being converted into a value added product here. So here uh, we have to take what is happening till the slaughtering of the animal, and once the skin is taken, it comes to the leather processing industry. So there they have a different process, that is the core process. I'm not going in depth into that. And whatever, when the core process is being done to manufacture it from the skin to the leather, so that whole process, there are a lot of chemicals, there are a lot of thermal treatment, there is a lot of energy that is consumed during the process, there is a lot of emissions that is happening, the waste water, the solid waste, all these things are there. So the downstream process is whatever the waste that comes out of during the process, and as a product when it comes, how it is being used, how it is being recycled. So all these are the things that we need to have a boundary. Next slide, please. I'm just explaining so that you will understand the concept to write a proposal actually. So when we look at the life cycle assessment, as I told, it is from the cradle to grave. So as I told, the raw material extraction, right, sourcing of the hides and skins, how much emissions in terms of methane that has been that is happening, and for transporting from the slaughterhouse to the actual production center, that also will be taken into account, and the actual process that is being done for converting into a leather, that is there are a lot of steps that is involved, which will consume a lot of electrical energy as well as thermal energy. So how much emissions that it consumes, and finally how that after the leather is being traded during the while using the leather in terms of a bag, or in terms of a car upholstery, or in terms of a footwear, whatever it is, after using it, how it is being disposed into a landfill. So this all end of life emissions also matters here. Next slide, please. So here when we look at, as I told, the one is the leather industry is a very traditional industry, and it is a challenging one because there are multiple stages, and there is no proper if we look at in the European industries, they have farming next to the tanner actually, but here the farming is done in one place, the slaughtering is done in one place, the production is done in one place. So from uh, the farming till it reaches the um, production center, I mean the processing center, in fact this raw material traceability is one which is very much uh, the leather industry is looking forward for a proper identification of the origin of that material. That is one area which is very good for writing a proposal as well. So here the complexity is one, as I told, collecting the data is a challenging one in terms of the leather carbon footprint analysis, and there is a lack of real-time monitoring, like during the process how much energy has been emitted when the processing drums are being used. They don't have a proper source of energy. When you look at an automobile industry, it is a well automated industry, I should say, but when it is a leather processing, it is still a very traditional, and lot of scope is there for putting all these technologies to make it more greener. So this is the one way challenging, but lot of opportunity for people to work on to get to make it more viable place. Next slide, please. Next slide, please. Okay, I've just given an example here, like from raw material to the when it comes to the processing industry by transport mode. This is actually an example taken when we did a manual calculation. Actually, we had a team working on carbon footprint, and in fact, they were working on, for example, if the leather is used as a car upholstery. This is one industry which is very in the upmarket. So try to see how much carbon dioxide emission is being done when we are transporting the raw hides and skins to the processing industry. For example, it is the calculation manually it was done, and it accounted as 0.6 kg of carbon dioxide. That is the contribution that it happens as a byproduct of the meat industry. Next slide, please. This is at the, when we see the raw material acquisition, it is the cradle stage. So the actual processing stage, when we look at processing the hides and skins to the finished leather, it is approximately, it accounted to 2.5 kg of carbon dioxide. And whatever wastewater, all these treatments, it was around 0.3 kg of carbon dioxide was what was estimated. Next slide, please. So when we after making it into a leather, we have to convert it into a upholstery. Like you need to do a stitching of that car seat. You need to have a cutting and sewing that leather as an upholstery, and then these leather has to be transported to the car upholstery has to be transported to the assembly plants, that car production center. So these all contribute to CO2 emission, and it was actually estimated as 0.4% of the total life cycle emission. Next slide, please. So in terms of when the car is being used, the car seat has been, the leather has been put as an upholstery, and the car is being used. So there is an indirect impact of the upholstery on the vehicle fuel efficiencies actually. So here, when we look at overall contribution of the CO2 emission represents actually as 45.3% actually. Next slide, please. So once the car is used, we are not going to use it anymore. Then we are going to dispose that upholstery. Either it can be a landfill or incineration. So the incineration emits around 1.1% of the total life cycle. So this is what the calculation showed. Next slide, please. So these are the key findings. What is that when we look at the cattle to grow, I mean cattle to grave thing, approximately 17 kg of leather, carbon dioxide of leather from after of the leather after the slaughterhouse stage. And when we look at the cattle farming is emitting a lot of emissions. More than the processing stage, the farming, the upstream process is having a lot of emission. And similarly, after the leather is being made as a upholstery during the vehicle usage, how much when we see it is it's more than 45.3%. So when we look at the production and the processing stage, it is both showing as 36.5%. So these all calculations, it was an example that was taken for identifying the different stages, how much it is contributing in. And this kind of thing, when we do very much manually, it is like it's not transparent, and there is like no auditing kind of thing we cannot do, because it is all like this drum runs for this hour. So this drum, when it runs for this hour, this much energy it consumes, and this is what the carbon emission would have been. So a lot of assumptions are being done to come out with this calculation. So this is a actual scenario of a leather processing and a leather product industry, that is uh, in real scenario, this is what is being done for a carbon footprint monitoring. So how should we do with the technological assessment? I'm just giving a framework. Next slide, please. Next slide, please. Okay, so here, as I told, the first thing is we need to have a IoT sensors that needs to be deployed for, that is the first step. So how this energy consumption can be tracked is by deploying the IoT sensors at every stage, like right from the machinery operations, whatever the drums that are being used, so that it provides a precise data on the electricity that is being consumed. This is first thing. And similarly, we need to have a sensor for recording the water usage. How much water is being used for this particular process, and what is the chemical dosing that has been done, and all these how much effluent has been let out, and what is the emission that has been uh, emitted. I mean, how much carbon dioxide has been emitted during. So that this all needs to be recorded with the sensor, so that we will have a real time tracking actually. So this is one thing which needs to be done, and it gives a lot of scope for it. As of now, there is only assumption based data. Like as I told, there is no real data that has been, I mean, this kind of real time monitoring has not been done, and this needs to be done. And uh, we can take any industry and we can do this kind of data to track the process, to monitor the process actually. In terms of when we say in because the lot of thermal treatments, like how certain operations requires a lot of heating, like they use hot water for dissolving dyes, dyeing operations, all these things. So temperature, how much temperature they are using for that, what is the humidity that is being maintained, what is the air quality that has been there in the processing, inside the processing industry. Is there any volatile organic compounds that is being emitted during the finishing operations? So all these are very important things. And similarly, the supply chain traceability is one very area where nowadays people use RFIDs tags after the leather is being manufactured. But at the raw material stage, the process is still like not well defined, and it needs to be uh, taken care in a better way actually. So that this is an area, I mean, an opportunity to see how it can be digitized. Next slide, please. So this is just an how it can benefit. Like when we do continuous sensor-based monitoring, definitely it minimizes the estimation errors, and today, as I told, it is only a manual measurement approach. It is based on assumptions. So here, the real-time auditing actually it will actually, as I told, it will showcase how the energy can be reused, how the water, if there is any water over usage or anything, how water efficient technologies can be developed. It leads to a lot of interventions in terms of process when we analyze these data. Next slide, please. So this is basically a 4-layer IoT. I can say you have to integrate into ERP for carbon footprint monitoring. Here, the first layer is the smart perception layer. So as I told, we need to use sensors for intelligent identification, tracking, and monitoring. So this will actually do a real-time collection of energy consumption and emission data. If there are any machineries, equipments, so all these needs to be calibrated as and when it is required. We can use blockchain enabled certification for these calibration so that it is authenticated well. The next layer is the adaptive data communication layer. So whatever data the perception layer has with the IoT devices, we have to transfer it to the data communication layer, and here we do the real-time monitoring of the environment impact. Next slide, please. So the third layer is the intelligent platform layer. What I mean to say is we will actually do a inventory analysis of the product's life cycle, like whatever we discussed now. Like in terms of process module, we break down the process flow, identify the hotspots where energy efficient methodologies can be used. So this entire data, what we have collected, we can have a database for it so that it can be integrated with the existing ERP systems, so that whatever procurement that we do for raw material, whatever orders that we manage, and how the energy has been utilized, so all can be integrated into one particular system. And here we can use AI models uh, to do the predictive analysis for carbon footprint forecasting also, and circular economy, that whatever is there any way forward to recycle this or reuse this materials what has been let out as a solid waste things, or in terms of wastewater, if it can be treated and reused. So these all uh, can be analyzed and utilized in a proper way. Next slide, please. So the final layer is the cognitive application layer. That is the here only the AI powered decision support systems, like we can identify the various renewable energy sources for areas where the emissions were high, and we can suggest the optimize the production, how it can be optimized in terms of transport. Yeah, if the routes can be optimized, the fuel consumption can be optimized. Is there any way for recycling, and how we can minimize the peak hour, or if there is any machineries that is uh, ideal, that how we can minimize the ideal time, and how that energy can be utilized in a better way. So it suggests basically the eco design alternatives, and it recommends a better logistic routes, and a green, how to identify the green suppliers. So here basically we will uh, come up with a sustainable dashboards for so that the employees who are working also are getting aware that we need to have a sustainable framework in our system. Next slide, please. So this is the data analysis. So whatever data we have collected using the IoT, here we continuously track the emission activities. So what we will do is like if there is we have lot of machineries in the leather processing industry. So if any machine fails, then the process production gets affected. So we need to ensure that the equipments are properly calibrated, if, preventive maintenance are being done properly. So as I told, when there is a machine that is in an ideal condition, that time we can propose that a preventive maintenance can be done. Nowadays, even for doing a scheduled maintenance also, instead of waiting for that particular time frame, we can even use the ideal time to maintain that, so that the downtime and associated emissions can be reduced. And as I told, this transportation and logistics are one of the important things in carbon footprint monitoring. So how the raw material, when it is being transported, or as a finished leather from the processing industry to the assembling units, how the routes can be optimized, how the fuel can be reduced. So all these things are areas where the quantum machine learning algorithms can be employed to optimize the things. Similarly, we can even look at QML models for the any ways for recycling whatever has been let out as a in terms of water, in terms of solid waste, how it can be reutilized. So that potential, if it has, we can evaluate those things and identify and optimize the waste reduction strategies, so that the nowadays this material recovery and reuse is one area which the end of life disposals are being done. For example, even in Nike shoes and all, whatever shoes has been used, they actually have a not in India but in abroad, they collect those shoes and they give money for that, so that people to encourage people to give back their old shoes, and they take that and recycle it to make a new shoes. So this kind of end of life disposal strategies are being done by big brands actually. Next slide, please. So here I have given a strategy how we can use machine learning algorithms to estimate carbon emission monitoring. Like there are, as I told, different variables in terms of energy, in terms of materials, in terms of transport distance. There are a lot of carbon emissions that is there. So here we can use polynomial regression methods so that we can estimate from the real-time data for continuous monitoring of the emissions. So currently, these data are not there. So we need to first do a data acquisition using an IoT sensor. And once we have the data, we can have this kind of estimation. And then we can have carbon emission based on the historical data, whatever process that they are following. If they have that history, then we can predict what is their carbon emission uh, for that particular data. So this will give leads to how energy consumption pattern over the time, whether they have reduced it or whether they are making more energy, if it is an energy efficient process. So this gives a lot of inputs for the industry to have a awareness about their process. So this can be done. Similarly, different sources of emissions, like and we can even identify the key factors. What are the key factors that are contributing to the high emissions? We can use decision trees for that and determine which manufacturing process contribute most to the overall emissions. Next slide, please. Similarly, we can use support vector mission. For example, as I told, there will be period of high, low emissions. So we can classify the data into different categories, and we can identify the periods of high emission in a production facility so that it can be balanced actually. These are areas where a lot of work can be done. One of the important thing is this volatile compound calculation, the VOC concentration from the chemical inputs. Predicting the VOC concentration is one of the very important thing as far as the leather processing industry is concerned. So here we can use regression algorithms to predict this kind of thing. And similarly, when we look at the, when we combine VOC, water, energy, all three multiple variables, we can even think of using these three together has a very non-linear relation. So here, between the production parameters and the CO2 emission, how it is being done. We can use random forest and gradient boost trees for this. Next. So we all know, like in all many industries, they have different production batches. So we can even estimate whether different production batches has different emission pattern, or we can have a clustering of this emission data to detect the anomalies, like whether there is any unusual spikes in a particular process, like finishing or beam house, or in the process, tanning process, which process has the unusual spikes, why is it spiking? So we can have a k-means kind of clustering of this emission data to detect these anomalies actually. Similarly, we can use neural networks for a combination of factors like what is the production volume, energy use, raw material. So all put together, we can have a complex, all these are complex relationships, and this data can be utilized to predict the emissions using neural networks. Next. Next slide, please. So how quantum machine learning can be used is, yesterday we had a very beautiful session uh, showing an example of how to handle multi-dimensional correlations. So here, when we look at the emission factor and the real-time monitoring, the energy, chemical, transport, and VOC is a multi-dimensional correlation problem where we can use QML for that. And similarly, when we look at the optimization as a problem, we can think of in terms of transportation, the routes, the logistic routes, what is the load, what is the energy fuel mix that is being used. So which combination will reduce the emission? So this is an optimization problem that can be used. We can use QML for it. Similarly, for equipment monitoring, we can use, yesterday we saw SVMs, quantum SVMs. In fact, which requires when the dimensionality is very high, this kind of quantum machine learning algorithms play a vital role. Here, it is in real monitoring, we can see that the quantum, the data that is that we are going to do will be very high. So for these kind of things, to classify the failure states in a machinery, we can use quantum SVMs, so that it will actually have a earlier detection and reduced downtime, thereby lowering the hidden emissions. Similarly, end of life analysis is very important, so that we can classify the material recovery paths, how a recycle, reuse, and a landfill, which combination will give a better end of life analysis is one thing. These all are very important for circular economy, so that by maximizing the recycling efficiency, we are trying to improve the carbon emission. Next slide, please. So there is a always yesterday also, I think there was a question when to use machine learning, when to use quantum machine learning. So when we saw yesterday for the iris problem, the machine learning algorithm was giving a better accuracy when compared to a quantum machine learning algorithm. Basically, when we look at why it is happening is, the data that the iris data, what we saw is a very straightforward small data set which has a clear distinction of the different patterns that is there. So in those cases, the classical machine learning algorithms work. But when there is a complex data with a high dimensional data, definitely a quantum machine learning algorithm excels in that. So when we look at the carbon footprint monitoring, our data is complex and it is a high dimensional thing. So for these kind of problems, the quantum machine learning will be a better solution when compared to a classical thing, in terms of handling the data, in terms of forecasting it, as I told, for optimization, for anomaly detection, even for so all these things that we can use machine learning, we can use quantum machine learning. But when we look at how these two technologies in terms of its maturity, we have heard a lot of lectures and we have seen that this classical machine learnings are production ready. But when it comes to quantum machine learning, the hardware is it's still in an experimental stage, and once it matures, once it is thing, definitely this will have a potentially faster. Even nowadays, the chips that are being developed are they are considering it to come up with a greener technology. So it will, as the hardware matures, this quantum machine learning will be a way forward for carbon footprint monitoring. Next slide, please. So basically, the benefits of using machine learning and quantum machine learning is both will have definitely it will provide a high accuracy in terms of emission measurements and predictions, and it can handle large volumes of data from diverse sources. So the efficiency of data processing and analysis will be more efficient, combining with the IoT sensor kind of interventions, uh, enabling a faster decision making. And these all are associated with reducing the cost that is involved with the manual monitoring and reporting. As I told, eco labeling is very important, and transparency in defining that is very important. And these technological advancements will definitely be a way forward for it. Next slide, please. Yeah, I just want to thank you, KCG College, for the opportunity given to me. So the future of the humanity and the planet lies in our hands and in the hands of today's young generation. So let us ensure that the creation of better world one step at a time. Thank you all for your attention. Thank you.
Any question answer sessions by the participants? You can, ma'am, one message is there in the chat box.
Okay. Can you?
Yes, ma'am.
Yeah.
They are asking to provide, if you could please provide the information about the funding agencies in the sustainability area.
Yeah, definitely. There are a lot of scope. As I told, this leather processing industry is not only the industry. Yeah, there are a lot of industries that are looking forward for carbon footprint monitoring. There are a lot of softwares that are available, but actual real-time collection and monitoring together, I'm not sure how many industries have come up with that kind of thing. So this is a way forward for us to take up and do. I will share definitely the funding opportunities that are there. You can now. This is the hot subject. The I think Dr. Deepa has rightly taken the thing, and combining with the latest technologies is the way forward for you to write the proposal. I've just given a very broad overview of so that you can understand when you write your proposal. This is not a very practical section, but it is a session for you to understand the problem and how you can take it forward to get a funding for your thing. This can be done for any industry. Yes, I will share that is there with Dr. Deepa too. She can post it in the group.
Yes, sure, ma'am. Any other questions from the participants? I now invite Renuka to give the vote of thanks. Madam, could you correlate quantum computing with healthcare applications? This is one question posted now.
Oh, yeah, we can actually. See, yesterday we saw like quantum evolutionary inspired algorithms for feature selection, even for classification. You have a lot of uh, machine learning algorithms are there. Uh, as I told, see what we can understand is yesterday sir showed one example of iris where the classical machine learning algorithm was performing well. So what is required for quantum machine learning is your complexity and high dimensionality data. Definitely healthcare applications will have that kind of uh, areas where the complexity is more. Any other questions?
Renuka, you can do the vote of thanks now.
Yes, ma'am. Now, on behalf of the organizers, it is my privilege to deliver the vote of thanks. I extend our sincere gratitude to both our esteemed speakers for today, Dr. Malati Jawahar and Dr. Priyanka Kokil, for sharing their expertise and enriching us our understanding of quantum technologies and their applications in sustainable solutions. We also thank all the participants for your active engagement and thoughtful questions, as well as the organizing team and technical staff for ensuring the smooth conduct of today's program. With that, this concludes the day 5 of Faculty Development Program. We look forward to seeing you all tomorrow again at 2 p.m. for day 6. Thank you all once again and have a pleasant evening. Thank you.
Thank you all.
Thank you, ma'am.
Thank
Thank you for spending this time with us today and hoping to collaborate with you in the future too. Thank you. On behalf
you.
of our management and faculty coordinators, a special thanks. To
Thank
the
you all.
participants, please do join back tomorrow. Tomorrow is the last day, and we have the test also. So the tested time will be posted in the WhatsApp group. So please be updated regarding the tested time, and the attendance link will also be given during the validatory session. And also we have the feedback, overall feedback also will be shared during the validatory session. All of you are requested to attend the validatory session, and orally we'll be asking a few of you to give your feedbacks. So please be prepared. And tomorrow we'll be taking a photo session also. So that you can switch on your video also. So be prepared. Thank you all of you. Good night.